Welcome to Chapter 2 in Algebra 2a. The beginning portion of Chapter 2 talks about representing relations and functions. And so in Chapter 2 we're going to start to get into this idea of linear functions and looking at those linear functions and how they relate to a graph and what they look like and some of the attributes of those, including slope and y-intercepts. We're going to be reviewing some concepts about linear equations over this chapter, and so most of the things that you're going to be seeing here should be reviewed for many of you, but understandably it's been a while for some of you. So as we go through some of this material, it may seem new to you, but it should be a review. First of all, start off with a relation. A relation is a mapping or a pairing of input values with output values. Relations can take on a number of different forms. They can be in the form of a table, where you can have x's and y's, like 4 and 3, 5, negative 2, 8, negative 6. You could also represent a relation as ordered pairs, like 4, 3, 5, negative 2, and 8, negative 6. Eventually, we'll also talk about representing a relation as a graph. And so each of these numbers can be placed as an ordered pair. For example, the first, and I'll not graph all of these, but the first point 4, 3 can be represented as a point on a graph as the point 4, 3. Again, 5, negative 2 can be down here someplace. And so we can represent a relation as a graph, a table, ordered pairs, and then we'll also talk about this idea of what we call a function mapping or a relation mapping, where you have your inputs here and your outputs here, and my inputs were 4, 5, and 8. And in this case, my three outputs were 3, negative 2, and negative 6, and then you can represent, the ordered pair 8, negative 6 as 8 goes to negative 6 by using the arrow feature. So we call that a mapping. Again, we can represent it with a mapping, an ordered pair, table, or a graph. All right. The domain is the set of all the input values, so essentially those values in the first column here. The domain would, in this case, would be 4, 5, and 8 for our example here. The range is the set of the output values associated with my relation, so negative 2, negative 6, negative 2, and 3 if I want to put them in order. A function. Now, a function is a very special type of relation. Again, realize it says here it's a relation. So first of all, a function is a relation. It's a very special type of relation in which each input has exactly one output. So each one of the inputs in our input table, and again, our inputs are our x's, and our outputs are our y's. So each one of these inputs in the first column has exactly one number that it outputs to. So 4 maps to 3, 5 maps to negative 2, 8 maps to negative 6. We see that in whether we use our table, our ordered pairs, our graphing, or our mapping function over here. But each individual input has exactly one output, and we'll expand on that here in just a few moments. An equation in two variables. So far we've looked at equations in one variable in the first chapter, and we were solving those equations in one variable. There was one answer for that because there's a set value that this equation is equal to. When we're looking at equations in two variables, however, now we're looking at graphing some sort of an equation that relates two different variables. Okay, so we're relating two different variables like x and y. So for example, 5x plus 2y is equal to 10. That's an equation in two variables because it has two variables, an x and a y. There's an independent variable and a dependent variable. The independent variable is also referred to as the input variable, and always and forever and ever that is the horizontal axis, that will be our x's. All right? And the y's will then be the dependent variables. So the dependent variables or the output variables, those are my y's. All right, so on my graph here, my y-axis depends on the value of x. And finally, a linear function is a function that can be written in the form y equals mx plus b, where m and b are constants. And eventually, we'll learn more about what m and b are. Hopefully, you already recognize that m and b are slope and y-intercept. But if not, we'll get into that in the next lesson. So what we want to do now is we want to start talking about representing relations. And so as we talk about representing relations here, representing relations, it says a relation can be represented in the following ways. It can be represented as ordered pairs, tables, graphs, or a mapping diagram similar to what we talked about before. So those are the four primary ways that we can represent a relation. Notice each one of these pictures shows the exact same ordered pairs. Each one of them shows the same input mapping to the same output. -2 maps to 2. Here's -2 maps to 2. Here's -2 maps to 2. And here's -2 mapping to, whoops, I'm sorry. Undo that. Here's -2 mapping to 2. All right. Now, on the top of the next page, then, we're going to go ahead and we're going to take a look at identifying which of these are functions. So if we're using this mapping diagram, again, the definition of a function is that each input has exactly one output. And again, exactly one output says that it can't have 0 outputs, it can't have 2, it can't have 3. Each input has to have exactly one output. So when looking at our first here, we can see that -2 maps to -1. -1 maps to 0, and 3 also maps to 0, but each individual input here maps to the exact same output. That's okay. It's all right for different inputs to map to the same output, and obviously 6 maps to 4. The relation is a function because each input is mapped onto exactly one output. Now how about letter B? In letter B, you may be seeing this right here. And this is the big no-no here. You'll notice that 2 is being mapped to 2 different numbers. The input of 2 has 2 different outputs. And because 2 has 2 different outputs, we would say in this case that this is not a function. It is a relation. It is a relation. But it's not a function because the input 2 is mapped onto 2 different numbers, 2 and 3. So why don't you try the next checkpoint exercise. If you need to draw a mapping diagram of it, feel free to go ahead and draw a mapping diagram of it. And then we'll take a look at our results in just a moment here. So taking a look at this checkpoint problem, what we want to do now is, in order to be consistent with what we've done before and make things a little bit easier on ourselves, we're going to go ahead and draw a mapping diagram with all the inputs. So again, my x's are my inputs. Another way to talk about my set of inputs is my domain. And so let's just list all the numbers that are in the domain. -5, -3, and 0. -5, -3, and 0. And then we're going to go ahead and graph our outputs, or what we refer to as our range. And the numbers in the range are 2, -1. We've got 2, -1. We've got 0. We already have a 2 in our output, so we don't have to write it again. So we've got a 2 here, and then let's go ahead and put our 5 in here. So now we've listed the inputs and the outputs, and now let's go ahead and make our mapping. -5 maps to 2, so -5 goes to 2. -3 goes to -1, pretty straightforward so far. 0 maps to 0, all right, 0 maps to 0. 0 also maps to 2, and some of you guys right now are seeing the big red flag coming out. 0 also maps to 5. Where's the problem here? Well, the problem is that 0 is mapping to 3 different numbers. And so because the input 0 has 3 different outputs, we would then say that this is not a function. Now, you can do this problem without showing all of this. Really, the big thing is taking a look at this individual, each individual ordered pair, and recognizing the fact that the ordered pair starting with an input of 0 and 0 and 0, right? So in this case, you have the input 0 showing up 3 times, and each of those cases, it has a different output. And so because of that, we know that this is not a function. All right, so whenever we have a graph of a relation, we can always take a look at a picture of that, and we can say that a relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. So if we have a graph of a relation, we can check to see if it is a function by simply drawing a vertical line anywhere through the graph. Any vertical line that I draw through this individual function here, or this individual relation, I suppose, every vertical line that I draw here only intersects the graph in one place. And so because of that, this is a function. In the next example, you'll see this is actually what we call a hyperbola. when I draw a vertical line through this graph, you'll see that it intersects it in two different places. And so because of that, this is not a function. Now, what about that picture makes it not a function? Well, let's look at these two values here. This happens to be the ordered pair 2, we'll call it 1.8-ish, I suppose. When x is 2, y is about 1.8. It's pretty close to 2. For the purpose of the video, we could probably also just call it 2. And then we have this point here, which is 2, negative 1.8. And so we can see that the input 2 has two different outputs. The input of 2 has two different outputs. And so because of that, we can say that this is not a function. Okay, so in looking at the vertical line test then, we want to take a look at this graph and say, is this first picture a function? And if I look at each one of these points, and I draw a vertical line through each one of these, you'll see that each one of these vertical lines does not intersect more than one point. And so because of that, the first example is the graph does represent a function because no vertical line intersects the graph at more than one point. Sorry, handwriting's a little bad there. All right, so how about the next one? This one does not represent a function. And it does not represent a function for a couple of points. Namely here, when I draw this vertical line, I'll see that I hit 2 points. And here, I see that I hit 2 points. Now the two examples I did up above were curves. So we could see pretty easily that it hit the curve in two places for the hyperbola example that I did on the previous page. In this case, we just have to check each vertical line and take a look, does it cross at two points? And so there are a couple different points here at x equals 3 and x equals 6 where the line will intersect at more than one point. So this one is not a function. All right, so how about graphing equations in two variables? Now, some of you guys remember some things from Algebra 1A, and so if you already kind of get some of this, this might actually be a little bit easier than we're making it, but to graph anything, if it all else fails and you've forgotten about things called slope-intercept form, you can just construct a table of values and then plot enough points from the table to recognize a pattern. Again, these are linear functions, so they should be graphs of lines in most cases. And so, in everything we do in chapter 2 anyway. And then connect the points with either a line or a curve. And like I said, all the stuff we're going to do in chapter 2 is going to relate to lines. When we get to things in chapter 5 and chapter 4 and 5, we're going to be looking at other things like parabolas and things of that nature. But most of the stuff we're going to be doing for right now, you'll be graphing a line. So to graph the equation y equals negative 2x minus 2, some of you guys recognize that this equation is in slope-intercept form, and the slope would be negative 2, the y-intercept would be negative 2. So for some of you, you can graph this without constructing the table. For those of you that cannot, we're going to go ahead and make a table. And so we want to say, we're going to make a table here, and I'm going to do mine this way. It's a little easier. I want negative 2, negative 1, 0, 1, and 2 for my inputs. And then I'm going to take this expression, negative 2 times x, which in this case is negative 2, minus 2. I know there's a lot of 2's in that problem, so the next one will be a little bit more clear. Again, the expression is negative 2 times negative 1 minus 2, negative 2 times 0 minus 2, negative 2 times 1 minus 2, and negative 2 times 2 minus 2. And again, all we've done here is we've taken these values of x and plugged them in here. And the original expression said take whatever x is, and plug it in to negative 2x minus 2. All right, so now we have to do some evaluating. Negative 2 times negative 2 becomes positive 4, and 4 minus 2 is 2. And the next example, negative 2 times negative 1 becomes positive 2. And negative 2 times negative 1 being positive 2, 2 take away 2 is 0. In the next example, negative 2 times 0 is 0, and 0 take away 2 is negative 2. Negative 2 times 1 is negative 2, minus 2 more becomes negative 4. And finally, negative 2 times 2 is negative 4, negative 4 minus 2 more is negative 6. So then we're going to go ahead and plot those points. So negative 2, 2 to the left and up 2, negative 2, 2, negative 1, 0, 0, negative 2, 1, negative 4, and 2, negative 6 would be right there. And then we're going to go ahead and connect these dots with a line. Now, always use a straight edge. Okay, my computer has the ability to make a straight line, so I have a function for that. But use a straight edge when you create these lines so that you can get a better idea of where your points are. And so there's my graph. It says plot the points. Notice that they all lie on a line. And then connect the points with a line. So again, when you do that connection of those points with a line, make sure that you use a straight edge. You can use the side of your identification. You can use the side of your planner if you don't happen to have a ruler. That makes a real good straight edge. Okay? All right. Now let's classify and evaluate functions. Tell whether the function is linear, then evaluate the function when x equals negative 3. So in the first example here, it gives you this f of x notation, but really all we're saying is that y is equal to 6x plus 10. Okay? And so this is a linear function because its graph is going to be a line. And so it says it's in the form f of x equals mx plus b. Again, the big key here is that x is being raised to the first power. It's not being multiplied by y, and so therefore you're going to get something that is linear. So when I try to evaluate f of negative 3, I simply put negative 3 in every place here for x. So I substitute negative 3 for x. This becomes 6 times negative 3, which is negative 18. And negative 18 plus 10 becomes negative 8. The second function, g of x, is not linear because it has an x squared in it. So this is not a linear function. I'm missing an I in there. It's not a linear function because of the x squared term. Because there's a second power involved in the problem, this is not a linear function. When we start talking in chapter 4, this is actually going to be something called a parabola. All right, because it's a second degree or a quadratic equation. In any case, we can still evaluate its g of negative 3. So every place I see an x, I'm going to replace with negative 3. So I'm going to substitute negative 3 for x, and then simplify. Now, this is going to be a little shorter than just this one step, but it's negative 3 squared. Negative 3 squared is 9, so 2 times 9 plus, and then 4 times negative 3 becomes negative 12, and then minus 1. So 2 times 9 is 18. 18 minus 12 minus 1 more. 18 minus 12 is 6. 6 minus 1 is 5. And so the answer for this one is supposed to be right there, but it's 5. All right, so that's g of negative 3. What we're really saying here, again, the y value at x equal negative 3 is 5. And that's what g of negative 3 equals 5 means. All right, so a couple of checkpoint problems here. There's like 4 of them, so give these a shot and go ahead and start your video again, and let's see what we can come up with. In number 2, this does pass the vertical line test because every time I draw a vertical line through it, it only touches it in one spot. So this is a function, or you can say yes, it's a function, or is a function, however you want to do it. For number 3, to graph this equation, we'd make a table. Here's x, here's y, and we really only need to pick a couple of points here. Let's try like negative 1, 0, and 1. That's usually pretty easy. And so this is 2 times negative 1 minus 3, 2 times 0 minus 3, and 2 times 1 minus 3. And I apologize, those 3's are kind of difficult to read, but basically we're taking 2x minus 3, and we're taking these values of x as my inputs, and I'm inputting them into the expression and replacing the x with those inputs. In any case, this is 2 times negative 2, which is negative 2, minus 3 more, which is 5. And so I kind of ran out of space here, so we're just going to go ahead and plot them as we go. This is negative 1, 2, 3, 4, 5. There's negative 1, negative 5. When x is 0, okay, when x is 0, this becomes 2 times 0, which is 0, minus 3, which becomes negative 3. And so 0, negative 3 is on my graph. And then finally back to here, when x is 1, 2 times 1 is 2, and 2 minus 3 is negative 1. And so when x is 1, y is negative 1. And I'm going to use the line feature here that I can do on mine. Obviously, you guys would get a straight edge at that point and do your best at connecting those points to make a straight line. Okay, so there's your graph of that one. How about number 4? Tell whether or not it is linear. Because of the third power here, this is not linear. And it doesn't matter that it's not linear. You can still do f of negative 1. I'm going to use some of this space up over here. F of negative 1 equals 2 times negative 1 to the third power plus 6 minus x. Now be careful with that because you're subtracting x, and x is negative 1. So I'm just going to put it in parentheses for right now. All right, now we do powers first, so this becomes negative 1 to the third, and negative 1 to the third power is just negative 1. So 2 times negative 1 plus 6, and then let's deal with this now. What's minus a minus? Well, we know that turns into a plus. 2 times negative 1 is negative 2 plus 6 plus 1. This becomes 4 plus 1, which is 5. And so we can say that f of negative 1 equals 5 because when I plug negative 1 in to that function f, it's 5. How about g of negative 1? Well, first of all, because this is x to the first power, this is linear because it's going to make a graph of a line because x is to the first power. And so now we can go ahead and evaluate what is g of negative 1. Well, that's 4 times negative 1 plus 9. 4 times negative 1 is negative 4, and negative 4 plus 9 is equal to 5. Boy, we're not getting a lot of variety for answers here. They're not always 5, but they just happen to be in this example. So that concludes our video lesson for lesson 2.1. Hopefully you've enjoyed that and got something out of that. And then we'll talk about questions that you may have tomorrow.